This is Nanoscape. I'm Seth Zimmerman.
And I'm Erin Spain.
On this show, we venture into the frontier of nanotechnology.
With experts in the field who are turning the science of small into the next industrial revolution.
This podcast is brought to you by the International Institute for Nanotechnology at Northwestern University. Everyone, may the 4th be with you. Star Wars Day is here, and few stories have done more to shape how we imagine light as a form of technology. The Star Wars universe has given us some of the most iconic light technologies in science fiction, from lightsabers, holograms, planet-destroying super lasers, and more.
Here on Earth, scientists are not building lightsabers, at least not yet, but they are learning how to control light in remarkable ways by designing materials at the nanoscale.
Today, we are talking with one of those experts, Matt Jones, the Norman and Jean Hackerman Junior Chair of Chemistry at Rice University.
Matt earned his PhD here at Northwestern in Chad Merkin's group, studying DNA-directed nanoparticle assembly, and he did his postdoctoral work at Berkeley, investigating how metal nanocrystals transform and evolve at the atomic scale. Some of the current efforts in his lab include pursuing the mechanistic understanding of nanoscale processes with an ultimate aim of developing materials with novel properties that will have an impact in medicine, optics, quantum information, and energy harvesting.
We are happy to have him on the show to talk about his research and the future of light-based technologies and share our mutual love of Star Wars. Welcome, Matt.
Hey guys, thanks for having me.
So I have to ask you, before you got into the nano world, when you were still a kid, were you a Star Wars fan?
Enormous.
Okay.
Enormous Star Wars fan. We had the original trilogy, recorded from television.
Yes.
Oh my God. Me too.
On a VHS. It was a while before we got the actual box set. So we had just recorded it from it was aired during Christmas or something.
Sure.
And I watched it probably every weekend for I would watch one of the 3 original trilogy movies every weekend as a kid, to the point where I not only had the movies memorized, but the commercial breaks, because it was recorded
Yes.
from television. I had the commercial breaks.
You just
And
sing along the
McDonald's commercial,
jingles,
I could
yeah.
sing along with it.
Do you think stories like Star Wars, do they merely inspire curiosity, do you think, or do they actually help and scientists imagine new ways, and in your case, light and materials, how they can be engineered?
They are great entertainment. I think they can be inspirational. I actually think, sometimes what's fun about them is occasionally when I'm watching some of these, like a sci-fi movie or something, or Star Wars, I'll put on my scientist hat and think, well, what's wrong with this? It's clearly not feasible. But if you take it a step further and go, well, okay, this exactly as they've described it, it would never work. But what would I need to do to get maybe the concept to work, or the goal, or whatever? So it can generate new ideas and inspire curiosity. And if you don't take it super literally,
Yeah.
but you just kind of think, well, what would it mean for light to be powerful enough to be directed at something for it to cause, heating or damage or whatever, you can kind of get some inspiration from sci-fi things, I think.
We love having Northwestern alums, especially alums of Chad Merkin's group, on the show. Speaking of the Merkin group, what was your Northwestern experience like, and how has your research evolved from then to the work that you're leading now?
Well, Northwestern was a great choice for me. Initially, wasn't considering Chad as a mentor, but he's very good at science communication. And I think he just roped me in with one of these project ideas that I was really fascinated by.
I'm curious, what project was it that roped you in?
Chad's group is really well known for having DNA functionalizing different metal nanoparticles. And one of the properties of metal nanoparticles is that if you hit them with light, they will convert some of that light to heat. Okay, so they can heat up. And there are people who have used this kind of in a brute force way. Like if you get nanoparticles into a cancer cell and you hit it with light, you can heat up the particles and heat up the cell and kill it. But his project idea that I was interested in was kind of a more gentle approach, where we're going to put DNA on a nanoparticle, hybridize it with a complementary DNA strand, and then generate just enough heat to dehybridize it to break off that complementary DNA strand and release it into the environment, which could be like a drug delivery kind of platform. So I had read a bunch about this, and that project was something that I just found really, really fascinating. And that was my first paper in the Merkin
Wow.
group. I ended up pivoting and working a little bit more on some other things like assembling nanoparticles using DNA. But that first project was how I first got introduced to the Merkin group and what really got me excited about it.
Your work now, you're studying again, as you said, nanoparticles, how they form and they assemble and create these collective properties. So I always like to know, when you zoom out, what is the main question that your lab is trying to answer?
The main question is really it comes from a observation that the early days of nanoscience and bleeding into today, a lot of the synthesis of a nanoparticle and the assembly of nanoparticles is understood very empirically, more like a recipe that you would follow, like a baking recipe. You don't know all the chemistry that's going on, but you know if I follow this list of ingredients, this process, I know I'm going to be able to bake my cake. A lot of nanoscience was that way when it came to synthesizing a particular nanoparticle. We knew if we followed this recipe, we used the right ingredients, we would get the particle that had been reported in the literature. But precisely why, the mechanistic question, why that set of ingredients, why that recipe, why that temperature, why does that lead to the particle that we see at the end of the day? Or in terms of assembly, we have these particles of different shapes, they assemble into this beautiful superlattice. Why? What is the mechanism behind that? What's going on at the individual level of particles? How are they rotating around each other, dynamically moving, dancing around in order to create this extended structure? Those kinds of deeper mechanistic questions is something that I think they're very difficult to answer. And so that's why they haven't really been explored in depth. But that's kind of the main thing that my group is working on, is trying to answer those really deep fundamental questions. It's very nerdy. I'm a huge nerd and
Love
I just sit
that.
there
Yeah.
and I'm curious and I just keep asking my students, "But why does this happen?
Yeah.
Why did that happen?"
Yeah.
And so that's, I don't know, that's my research program, is kind of curiosity based, mechanistic, trying to answer mechanistic questions about synthesis and assembly.
What is it specifically about light interacting with matter at the nanoscale that really makes this such a rich scientific frontier?
Yeah, I don't know if I can pin down one
Yeah.
particular reason, but it happens to be the case that a lot of different materials, when you shrink them down to the nanoscale, a few nanometers or tens of nanometers in size, they start interacting with light very strongly and in very interesting ways. That happens for semiconductor materials. So the quantum dots are one of the prototypical examples of this. You can take a material like cadmium selenide, which just looks like a dull gray blob with material at the bulk scale, and you shrink it down to little nanoparticles. And depending on their size, they'll emit light of very different colors based on their size. Same thing for metal particles, which is more of what I work with. We all know what a piece of gold looks like at the macroscopic length scale, but when you shrink particles down and you change their size and their shape, they can exhibit vastly different optical properties. And so the idea of assembling particles into extended structures, maybe those new structures can inherit some of those interesting properties that the individual particles have, but now at a collective scale. So that if you have a lattice of these particles that each individually have unique properties, that those will be able to couple through this periodic structure and give rise to some new properties.
And we're talking about using these materials in different areas like optics, medicine, quantum information, energy harvesting. Which one of these potential applications are you the most excited about right now?
One I'm excited about is a field called metamaterials. So this is, admittedly, the term is a bit ill-defined, but this is a class of materials that their properties are dictated by small nanostructures, what their shape is and how they're arranged. And what makes them really exciting is that metamaterials can exhibit properties that no naturally occurring material exhibits. So there's a property called the index of refraction that we use to describe how strongly a material bends light. Okay, and for every known naturally occurring material, the index of refraction is a positive number. But if you arrange nanostructures in precisely the right way, and they have the right shape, and they're the right size, and has to be in the nanoscale regime, you can generate a material which has a negative index of refraction. That is very bizarre. And if you build a material like that, you can, by the laws of physics, it's allowed, you can build something like the Harry Potter invisibility cloak. Yeah.
Ah!
So
Okay.
this
Okay.
is, believe it or not, that is fiction today, but a material which can bend light around an object and disguise it and camouflage it is allowed by the laws of physics. But typically, to do that, you need something that has a negative index of refraction. So only these metamaterial like structures are the only things known that can do that. And so some of the materials that we assemble in my group potentially have those interesting properties. They have the right structures, and we're still investigating this. So stay tuned, but maybe someday we'll have like a paint that you can paint a wall and it'll make it invisible or something, you know.
That's another
Uh,
episode. We're gonna be coming back to that one. That's
yeah, I'll
one
let you
where
guys
I
know when I'm invisible, and then we can have another podcast
There we
where
go.
you can't see me.
One of your recent papers that caught my attention was published in Nature Communication, and you explored these tiny gold nanoparticles and how they can have a left or right handed twist, even though the particles themselves aren't twisted at all. Can you explain what's happening there and why that kind of structure matters for how materials interact with light?
One of the structural properties of metamaterials that make them have negative index of refraction, one way to do that is for the material to be chiral at the nanoscale.
Okay.
So chirality is this special structural property where two objects are considered chiral if the mirror image of one does not superimpose with the other. So your hands are chiral objects. The mirror image of one does not superimpose with the other. And so a lot of every biomolecule in your body is chiral, DNA is chiral, your proteins are chiral. It's a very important property. It's very rare to see naturally occurring, I'm not sure of any examples of naturally occurring materials that are chiral at the nanoscale. But it turns out that chirality at the nanoscale is one way that you can get this negative index of refraction property, which, someday can make these really amazing invisibility materials or camouflage materials. So that paper, what was exciting about it was that we saw nanoparticles spontaneously assemble into a chiral structure. They assemble themselves into a chiral lattice. And so that is really promising for being able to build a material which has this negative index of refraction and build it in a way that is minimal human intervention. It literally is like you take a droplet of this material and you just let it dry on a surface and it forms this chiral arrangement. So as a technology in the future, it would be really exciting if you could develop a paint which you paint it on whatever surface you want to have this negative index of refraction property and you just let it evaporate and the particles in that paint spontaneously assemble into this chiral structure. That paper was more, again, getting to my nerdy self, trying to answer, well, why did these particles assemble into this chiral arrangement? It's very unusual to see that. The particles themselves are not chiral. There are no chiral objects in the system. Usually, if you see a chiral object, like a snail shell or something that's chiral, and you ask why, you can say, well, something at a smaller length scale was chiral. And why is that thing chiral? Something at a smaller
Okay.
length scale. And eventually you get down to a molecule or a protein. There was no example of that in this case. So there is no molecule. There's nothing at a length scale smaller than the nanoparticle that's chiral. So some new mechanism
Yeah.
had to be at play that gave rise to the chirality we were seeing. And so that paper was more about me being curious and a giant nerd and just wanting to know why on earth did these
Right.
particles choose to do this? And so it was answering that question. The excitement around it was that it had this potential to be a metamaterial to exhibit these interesting new properties.
When scientists say they want to control light with materials, what does that actually mean, I guess, in practice? What kind of technologies might come out of this research in like 5, 10, 15 years down the line?
One technology which is kind of exciting is something called a meta lens. So this is a lens made out of a metamaterial. So a typical optical lens is limited in what it can resolve by the wavelength of light. So there's this general rule that if I want to image something of X nanometers in size, I need to use a wave-like phenomenon like a photon that is similar in size to X. So for example, optical wavelengths of light are about 400 to 700 nanometers. So that means that if I'm using let's say 500 nanometer photon, it has a wavelength of 500 nanometers, a nanoparticle that's 50 nanometers will essentially, in a sense, kind of be invisible to that wavelength of light. Okay, so light can't see things that are smaller than its wavelength. That's called the diffraction limit. And so if I have a lens and I'm trying to image, let's say, a cell, and I'm using optical light, like 500 nanometer light, I'm not going to be able to image the parts of the cell that are smaller than about 500 nanometers or
Mhm.
maybe a couple hundred nanometers. And there's lots of stuff going on in the cell that's much smaller than
Okay.
that you would like to be able to see. Well, if instead of making my lens out of a traditional material, I make it out of a material that has a negative index of refraction, I can now defeat that diffraction limit. I now can image things that are smaller than the wavelength of light. Typically, if you want to image things that are much smaller than 500 nanometers or a couple hundred nanometers, you have to switch from using photons to using electrons, and they can interfere with the material. They can damage the material a lot more. So this is what an electron microscope is doing, is
Yeah.
electrons are much, much smaller in wavelength than photons are. So you can image smaller things. But we would love to be able to use just a benchtop optical microscope, be able to image nanoscale things, if only we had these meta lenses that had a negative index of refraction. So there's a potential future where an optical microscope might be able to resolve very tiny nanoscale objects if you had lenses that were made out of these negative index materials.
That would really democratize nanoscience, I would think, having, a benchtop microscope be able to do
Yeah.
that.
Yeah.
Just like
The
swapping out a
technology,
filter, just like, oh, I need this new one. Here we go. Just throw
I'm
in
going to
the
pop in a
the
new
Yeah.
lens.
50 nanometer one and we'll be good.
Yep, exactly.
No, that's very
Yeah,
exciting.
that would be very, very exciting. I'd love to be able to watch the individual nanoparticles as they move around and grow and change shape
Yeah.
and assemble. And that's very difficult to do with
Yeah.
electrons. But if you could do it with photons, that would be a huge advantage.
In your lab, do you think the best discoveries start with the phrase, I have an idea? Or do you really think it's, wait, that should not have happened?
I would say the best discoveries come from that should not have happened, the curiosity kind of thing.
Yeah.
I think a lot of people get hung up with their own ideas. They come up with an idea and it's, you kind of have some ownership of it. You feel like it's a great idea. And then you go into the lab and you try to make it work. It never works. It
Mm.
almost never works the way you think it will, right? The nature is so much more complicated and nuanced than we usually give it credit for. We usually appreciate when we're coming up with ideas. And I can think of many successful projects in my lab that were offshoots of something I had come up with. And the project really got started just by asking, well, why did that
Yeah.
happen?
That was
And
weird.
that was
Yeah.
weird. That doesn't make any sense. Why on earth is that the case? And
Yeah.
then you kind of dive into this thing, and what you end up finding is so much more interesting
Yeah.
and so much cooler than the idea that you initially came up with. And I think the science a lot of times goes that way. And most people don't really admit to it or talk about that component because, it makes it seem like your ideas aren't any good. So you got to have an idea. You got to have some
Yep.
direction that you're going to go in, right? And sometimes it works, sometimes it doesn't. But I think being curious and just letting the universe tell you what's interesting is sometimes a more successful route to discovery.
What do you hope listeners take away from this conversation about the nanoscale and what's possible in the future?
So there's all this promise of technology and advancements and new materials, but you need to lay the foundation with the fundamental science first before many of those things can come to fruition. There's a lot of things to be excited about in nanoscience, even if maybe you don't hear about it as much or don't see it in sci-fi as often as you
Yeah.
used to. That's just us scientists, us nerds working in the background. And in 5 or 10 years, you're going to start seeing these things come to fruition once the fundamentals have really been built up in the way they need to be.
Matt Jones, thank you so much for your insight today, sharing your research and playing along with some May the 4th be with you storylines here. We appreciate it.
Thank you guys. It was a lot of fun.
Thanks so much for listening. This podcast is brought to you by the International Institute for Nanotechnology at Northwestern University. Be sure to follow this show on Apple Podcasts or wherever you listen to podcasts, and be sure to give us a 5-star review.
For more information about IIN, go to our website, iinano.org/podcast.